Okay, hello, Honor Chem students. Mrs. Snyder here, and I just want to do a really quick video, just kind of going over the equilibrium expression. I know that you watched the Bozeman scientific expression or video that does talk about equilibrium expressions. If you haven't, you definitely need to go back and look at that, because I'm going to go over this fairly quickly and then just get into a little bit of practice with it, which the Bozeman video didn't quite have as much on that. So reversible reactions, we know from our first yesterday lesson is that reactions are reversible. You can go from reactants to products, but then you can also go backwards from products to reactants. And so we represent that with a double arrow right here. And we know that at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. And that's an important piece to know. The concentration of reactants and products are constant at equilibrium, but it doesn't mean they're the exact same amounts. So you're not going to have a 50-50 situation all the time. You might have, as the video the day before explained, a 20-40, or you might even have just a little bit of reactant and a whole bunch of product, or you may have a whole bunch of product or reactants and very little product formed. But the important thing to know is that you can't be at zero and still be at equilibrium. You must always maintain some amount of reactants in order to stay, or some amount of products in order to stay at equilibrium. Okay, so this is just another example of a picture that had a reaction of water reacting with carbon monoxide, and it's going to produce carbon dioxide in H2. And if you kind of look at this as a time frame, let's say this is at time 0 before you let this reaction proceed. You have just carbon monoxide and water in the beaker. Now, let's say after 10 seconds, we're allowing this reaction to proceed. You'll notice there's two hydrogen, 2 products formed, right? And there's also some carbon dioxide formed. There's only 2 molecules of each, the H2 and the O2. So let's say this is 10 seconds. Now we're at 20 seconds. Oh, look there's more H2 formed. There's 1, 2, 3, 4, 5, and there's 5 CO2s. And then at 30 seconds, the concentrations did not change. So that means we established equilibrium here at marker C. So whatever I said this time stamp was, let's say 20 seconds. Okay, so we established equilibrium because you'll notice that the concentrations do not change, but they are also not equal, but they don't change from this point forward. Okay. So I'm going to go through this. This is the law of mass action. You went through this very quickly, or you probably did watch, hopefully you didn't. If not, you should, the Paul Anderson Bozeman Science to explain the law of mass action. Okay, but here's where I want to get a little bit of practice for you guys. This is the equilibrium expression. It asks for you to write an equilibrium expression for the following reaction. And we're going to use that idea with the law of mass action to do this. So remember that a K, or that KEQ that we're going to write, remember that that is really a ratio of products over reactants. So the K, or we call it the KEQ, it's a capital K, would be the concentration of the products. So the product is HF, and do you remember we write concentration by using this bracket? Okay, and since there's a 2 in front here as its coefficient, that becomes the power. So it'd be the concentration of HF over the concentration of H2 times the concentration of F2, and that's how we write an equilibrium expression, just like that. Okay, it's the concentration of products over reactants. It's a ratio. Okay, but what happens if the equilibrium expression, let's say there isn't, let's say you have a balanced equation and it doesn't have, it has a solid in it or liquid. The question that I ask is, could they be part of the equilibrium expression? Could solids or liquids be part of the equilibrium expression? So let me give you an example here. So let's say that we have water. I'm going to have two water molecules, and I am going to do a dissociation here, or a decomposition reaction rather, of this liquid water, and I'm going to get two hydrogen gases then, and I'm going to get an oxygen gas. And now this is a balanced chemical equation. If I asked you guys to write the equilibrium expression for this reaction, would everything go into that equilibrium expression? And remember, the expression has to have concentrations. So clearly gases can be a concentration because they're the amount of particles that are in like a unit volume, they're in a container. But what about this liquid water? Is this a concentration? Think about that. What would be the solute? What would be the solvent if it was a concentration? And the answer is, this isn't a concentration. This is pure water, so there's nothing dissolved in it. So guess what? It's not part of the equilibrium expression. So if we were to write this equilibrium expression, it would be the KEQ is equal to the concentration of H2 squared times the concentration of oxygen. All of that, over 1. That's how we would represent that. What if you had something like A gas plus B gas? Oh, we'll say 2B gas. And, oh, by the way, I should have these both with double arrows. There should be a double arrow here too. What if we have something like this, A gas plus 2B gas, and we end up making AB2, and it's going to be a solid. So we go right from gases to solids. And I ask you to write that equilibrium expression. Okay, well, the KEQ would be the concentration of products over the concentration of reactants. Well, since this is a solid, it can't be part of the expression, so I'm going to represent that as a 1, and this would be over the concentration of A times the concentration of B squared, because it's to that power. And that's how you write that equilibrium expression. So just like you learned in the Bozeman science video here, this is the same kind of thing that's talking about what is favored. If your K is greater than 1, you think about that. If you have more products than you have reactants, your K is going to be greater than 1. And that's what we say is products are favored, or the forward reaction is favored. The reverse reaction is favored, then that means there's more reactants. And think about that. If you have more reactants here than you have products, your K value is going to be less than 1. And so then that means reactants are favored. And remember, just a good note to always remember, equilibrium expressions, you only put in the equilibrium expression things that are gaseous and things that are AQ, because both of these represent a concentration. Okay, so here's my question for you. What if I asked you guys to calculate the equilibrium constant? I give you a balanced equation, and it says it is determined that the equilibrium of the H2 is 0.1 molar, the F2 is 0.25 molar, and the HF is 0.052 at equilibrium. Calculate the KEQ, and then determine whether or not reactants or products will be favored. So you may see a problem like this in your homework tonight. How would you do this? I'm going to give you a hint before we get started. You're going to need to write the equilibrium expression. So go ahead, hit pause right now, and what I want you to do is to hit the write the equilibrium expression, and then I want you guys to solve for the KEQ and then determine if reactants or products will be favored. So hit pause now and see you in a few. Okay, welcome back. hopefully you wrote the equilibrium expression, which is right here. The KEQ is the concentration of products over reactants. They're all gases, so everything can be in the equilibrium expression. So it is the KEQ is equal to the concentration of HF to the second power over the concentration of H2 times the concentration of F2. And now what I did was I just plugged in the values that I had. The H2 was 0.1, the F2 was 0.25, and the HF is 0.052. This has to be squared, and I come up with 0.11. Now, I'm just going to warn you guys, because I've been doing this job for a while. A lot of times kids want to take shortcuts and they don't want to write the equilibrium expression before they plug in everything. I highly, highly, highly recommend you write the equilibrium expression correctly. And then that way, when you plug things in, you won't miss doing these powers, which sometimes kids do, and then you get the wrong answer. So, be careful for that. So you end up, in this instance, with a 0.11 as the answer. What does that mean? The KEQ is less than 1, so that means reactants are favored. I hope this helps. Hope you have a great day. And yeah, see you next time.